Knowledge is a tool, and like all tools, its impact is in the hands of the user. Dan Brown. Business logic is the reason why software is written. As the author puts it, a system's user interface can be sexy and its database can be blazing fast and scalable. But if the software is not useful for the business, it's nothing but an expensive technology demo. In this chapter, we will therefore introduce two patterns for simple business logic: transaction script and active record. Because these are patterns usually associated with object-oriented languages, like Java, I will be using a functional language instead, called EECCIS. The idea here is simple. Just because much of the literature in the matter was written years ago for these languages, it does not mean the lessons learned and taught cannot be applied outside of that context. By using EECCIS, I hope to help the viewer understand the deeper meaning behind each pattern, and that such knowledge is not dependent on a specific paradigm or programming language. As usual, adaptations must be done according to the context in which these patterns are being applied, but that is the crux of every good engineer. We do not simply copy-paste what we see, we understand it and adapt it to the environment. With this disclaimer out of the way, and in order to give the proper time and attention to each pattern, this chapter will be divided into several parts. In this first part, we will be discussing the transaction script. The transaction script organizes business logic by procedures, where each procedure handles a single request from the public interface of the application, also known as the presentation layer. Although these procedures can use thin abstraction layers to integrate with the database, such as lightweight ORMs, they usually interact directly with it. To make things more interesting, you can also use this pattern with other patterns, such as active record, which will be discussed in a future session. The only requirement procedures have to fulfill is to implement the transactional behavior correctly. No matter what happens, the state of the system must either succeed or fail, and it must be consistent at all times, hence the name of the pattern. This sounds easy, but in practice, there are several aspects one needs to have into account, especially when dealing with distributed systems. Let's have a look at a naive implementation of this pattern using a thin abstraction layer to talk to the database, called ecto, which uses the repo keyword to denote repository. This is how you manipulate databases using ecto. Here we update the users table and then insert a record in the visits log table. We can see how this works in real action by running the code. We start by showing the user record with ID 27, which we want to change. Then we run the code and successfully verify that both the user and visit tables were updated. However, the experienced viewer will notice that the insert and update operations are two separate statements. As a consequence, it can be expected that at some point in time an error will occur after the update operation succeeded and before the insert operation started or completed. As a result, the system will be left in an inconsistent state as the user's table will be updated, but the visits log table will not. Let's see this in action. I have updated the code to throw before the insert statement runs. Before running the code, we check the state of the database to have a starting point of comparison. Pay attention to the user John with ID 31. Now let's run the code in the terminal. As expected, the execution fails, and this failure leaves the database in an inconsistent state. The users table was updated, but the visits table was not. This function is not transactional. Let's attempt to fix that. If you are using a relational database with support for transactions, the fix is simple. We can bundle both operations into a single transaction, which will either succeed or fail, taking the necessary measures to ensure the database is consistent in case of the later. In our case, when using Ecto with PostgreSQL, we can make use of the repo_transact function, which will ensure the transactional behavior we are looking for. Let's once again see this in action, this time with the updated function, and then check the database as usual. Pay attention to the user with ID 37. Now that we have the happy path working, let's add a throw in the middle and recompile the code. When running the code, it fails as expected, but the database is still consistent, thanks to the transactional behavior we added. Life, however, is not always this simple. If your database does not have support for transactions over multiple updates, or you are trying to issue updates for multiple distinct storage mechanisms, the fix can go from slightly more complex to basically impossible. This is the case for distributed transactions. It is fairly common for an application to make changes to the database and then publish a message. Consider the following code sample. Here we first update the database and then try to publish a message. To see it in action, we will update the user with ID 45. We check the database and the message broker to snapshot their initial state. Then after we run the update, we can confirm the user's table was updated and that the message broker has a new message. However, if you remember our previous example, you will identify an issue here. If an exception happens after the database is updated, no message will be sent, and as a result, our system will enter an inconsistent state. You may think that we can make use of the repo_transact function we saw just earlier by wrapping both operations inside a function. This, however, does not really solve the issue at hand. This will only work for scenarios where we only send a single message to the message broker after the update to the database is done and a failure occurred immediately after said update. It won't work if another issue occurs after the message was sent, as this would trigger the rollback mechanism of the database, but a sent message cannot be unsent. The best scenario would be to send a new message that nullifies the old one, but that brings a host of new problems. Let's see this last use case in action by adding an error after sending a message to the message broker. First, we check the database, paying attention to the user with ID 47 and the queue to make sure it is empty. Then we run the code and see it fail as expected. Going back to the database, nothing has changed. However, the message broker has a message in the queue, which means the system is now in an inconsistent state. To address this issue, the author introduces the CQRS pattern in Chapter 8 and the outbox pattern in Chapter 9. For the time being, let's continue to explore more challenges with the transaction script. Not all examples of distributed transactions are as easy to identify, however. If your client, application, or database are in different machines, then you have a distributed transaction by default, as shown in the image. This is still the case even if the code is a simple counter update. From the perspective of the client making the request, the operation will be marked as failed if any of the following events happen. 1. In a REST service, the application sends the update request to the database, which updates correctly and then times out. 2. In a REST service, the application sends and receives a success acknowledge from the database, but then the application times out and the client does not receive the success response. 3. If the client and application are running on the same process, the application sends the request to the database, but then crashes before getting the success acknowledge from the database. In any of these examples, the counter was updated, but the client does not know about this. As a consequence, it is only natural that the client tries again, thus resulting in a system with an inconsistent state. This problem is, much like the previous one, impossible to solve. This is in fact an example of the two generals problem, the first computer communication problem to be proven to be unsolvable with a limited number of messages. As a result, the only way to fix this type of problems is to allow for operations to be repeated multiple times, but without causing changes to the system. In other words, the operations must be idempotent. There are two possible ways one can adapt the code to achieve this. The first one is to pass the value of the counter we want the database to use, as in this code sample. The second option is to use optimistic concurrency control. Before attempting to update the database, the client asks for the current value of the counter and then passes that as an argument to the update function. If someone else updated it in the meantime, the operation will do nothing, as the condition for equality won't be satisfied. The client can then try again later until a change is done. As we can see, the code for this check is rather simple. Both options provide an idempotent solution to the problem, at the cost of an additional read operation, which accesses the value of the counter before attempting any writes. The transaction script pattern is most effective for applications with simple business logic, and where code reuse and complex validation are not important factors. This pattern shines by its simplicity and modularity. However, as a system grows, it becomes more frail over time. Adding complexity comes at a huge cost due to the lack of reusability, and maintenance becomes harder as its architecture was not designed with scalability in mind. As projects grow, moving into other patterns, like the domain model, is usually advised. In regards to testability and analyzability, using this pattern should not produce any relevant differences. Overall, well-structured code in any pattern should be easy to both test and analyze, given the application's complexity matches the correct use of the pattern and that the proper logs and diagnostic functions are implemented. For more information about this, I recommend the paper Analyzing the Effect of Design Patterns on Software Maintainability, a case study presented in EECCIS 2018, where the transaction script was matched against 3 other well-known patterns: domain model, which we will discuss in the next chapter, service layer, and table module. This paper measured the modularity, reusability, testability, and analyzability of this pattern against the others, and the results, which we can see in these graphs, were rather interesting in my opinion. Modularity is increased at the expense of reusability, whereas testability and analyzability are not really impacted. An example of where this pattern can be used is an ETL, extract, transform, load application, where each operation extracts data from a source, transforms it, and then it either presents or loads the result to a different part of the system. An example where this pattern should not be used is in any complex system, such as the Academic Information System for the Institut Technologie Supérieure Nopember. In this study, the authors of Assessing the Impact of Enterprise Software Design Patterns on Maintainability, a case study, applied this pattern to the application and then measured the complexity of the code using a suite of several metrics. Since knowing how to not do things properly is just as important as knowing how to do them properly, let's have a look at what they learned. Please have in mind that the metrics used by the authors of the paper are good indicators that the pattern does not fit the use case. They are not infallible laws. As usual, you must use your understanding of the context and results produced by said metrics and the code and come to your own conclusion. The typical "it depends" as any engineer is used to. We start with a brief discussion of the Chidamber and Kemmerer metrics. These metrics stem mainly from object-oriented design, but they can still be adapted to other paradigms. Weighted methods per class, the number and complexity of all methods present in a class or module. Depth of inheritance tree, the deeper a module is in an hierarchy, the greater the number of functions it inherits. You don't need inheritance for this metric to have value. Simply consider that the greater the amount of functionality any given module imports from other in an opaque manner, the harder it will be to predict what it does. This is applicable to inheritance, obviously, but also to imports, macros, and other features languages have as well. Number of children. A great number of children or direct dependents that implement or extend some behavior from a parent module is a good indicator of reusability, but it is also a signal that the responsibility of the parent module is not abstracted well enough, and that other independent modules should be created in order to separate concerns. Coupling between object classes. Excessive coupling between modules is detrimental to modular design and prevents reuse. The more independent a module is, the easier it is to reuse it. Independent modules are also a good indicator that a good separation of concerns is being achieved. Highly coupled modules also make testing harder, as the number of modules needed to test any given features grows considerably. Response for a class. The larger the number of methods and modules involved in creating a response for a request, the greater the understanding of the system is needed to debug and test the entire flow. Lack of cohesion in methods. Also known as LCOM1, this metric states that the more cohesive the methods in a module are, the more cohesive the module is. A lack of cohesion implies a poor separation of concerns and an unnecessary increase in complexity. It is important to notice that this last metric has received a fair number of criticism and that subsequent models, such as LCOM2 and LCOM3, have been developed, with the latest recommendation being LCOM4, which was not used in the paper mentioned. Still, the original version still provides insightful information. With the definitions of these metrics done, we can look at the following delta table, where NP is the original version of the software, and PAT is the version where transaction script was applied. The specific calculations for each metric can be seen in the original paper, but the last column shows a chilling conclusion. With the exception of DIT and NOC metrics, which remain the same, every other metric increased in value, meaning the code became more complex and harder to maintain. And we have finally concluded. In this small essay, we learned what is the transaction script and where it can also be best applied. We also saw a couple of examples where it can be used properly and improperly, and we even delved into the Chidamba and Chimera C and K metric system to evaluate the refactoring impact of a complex application using this pattern. Consequently, it should be to no surprise that the transaction script pattern can be mainly used for supporting subdomains where the logic is not very complex. It can also be used as an adapter for generic subdomains or even as an anti-corruption layer, which we will talk about in more detail in Chapter 9. I hope you enjoy this more focused and shorter type of video. In our next video, we will delve into the active record pattern. If you would like to see more content like this, please feel free to like, share, and subscribe. I also want to give a big thank you to all the people that helped me get this far by answering my questions in community forums. This essay would not have been possible without your different viewpoints and experiences. I wish you all the best and hope to see you for the next section of Chapter 5.